Machine learning system design is one of my favorite aspects in machine learning. We start with a business idea, a product ideation, to deduce a whole set of technical requirements to build that product. I want to give you my framework, my playbook, to design ML solutions from a business problem. I'm going to use a specific example to illustrate this playbook, how to build the friend suggestion feature on Facebook. We are going to design the different components and look at how this can be framed as a machine learning solution. Let's get into it. So let's dig a bit more into machine learning system design. So machine learning system design is what is allowing you to architect your solution. There are many different levels to system design. So you can try to design things at a high level, such that you have an overview of the overall system, or you can design the little details of your systems. Here we're going to focus on the overview. We're going to focus on the high level. But everything that we're going to talk about can be applied to the little details. Also, what we are going to talk about today is what we are looking for in machine learning system design interviews. So if you are applying the framework that we're going to look at today when it comes to machine learning system design, you should be able to be successful in your interviews. So what are we trying to do? Well, we start from business requirements, and we're trying to establish some technical requirements to build a machine learning solution. So let me give you a playbook on how to solve the problem at a high level. So we start from business requirements. The next step that we need to solve is how to reframe the business problem into a machine learning solution. We should already know that there is a machine learning solution to that problem. But this is a time where we need to make sure that we understand that the problem may be a supervised learning problem, a classification problem, a regression problem, a reinforcement learning problem. So we need to make sure we understand what machine learning framework we're going to apply to the specific business problem. We need to understand the business metrics. So we need to understand what it is that we want to improve in the business. So we need to come up with a set of KPIs that make sense for the business. And as much as possible, we should try to understand how those business metrics relate to the problem that we are looking at. By having the right business metrics, we should be able to understand how the machine learning solution is impacting the business. It is not always easy to tie down a machine learning solution to a business metric. So this is not always a trivial thing. What are the online metrics? So when we're going to deploy models, we're going to need to assess the model in production. So we will need to be able to perform online experiments and to assess the quality of those experiments with online metrics. Online metrics allow to compare two models in production and to understand which one is the best based on the online metrics. So when we perform online experiments with production data, it is not always easy to tie down the online metrics to the business metrics. When we compute online metrics, we are using the data that is coming in real time. When we look at business metrics, we may need to wait for days, weeks, or months to actually see the actual results on the business metrics. So it is not always easy to correlate the online metrics to the business metrics. What are the architectural components of your system? Do you need to pre-process the data? Do you need to rank the data? Do you need to post-process the predictions? What database will you need to connect to make sure that you can predict accurately? How do you acquire the training data? So there's a lot of questions that need to be answered when it comes to what are the different components that will compose your system. How do we get the training data? So when we look at machine learning, we need to make sure that we have the right data to train the model. So how do we acquire the right data, and what is the training data looking like? Do I need to do some pre-processing on the data to actually get what is the training data? What is the instance label of the training data? So there's a lot of questions that need to be answered when it comes to what is the training data. What are the offline metrics? So we talked about business metrics and we talked about online metrics, but we also have offline metrics. When we train a model, we often assess the model on historical data. This is called an offline experiment. And in offline experiments, we have offline metrics to assess different models against each other. It is sometimes very hard to use the same metrics in online and offline experiments, so we need to come up with offline metrics that correlate well with online metrics. And it is not always the case. What are the features? So what data will you put into your model? With what data will you train? Often, as machine learning engineers, we want all the data possible. but we should be able to come up with a set of minimal features that can be useful for our models. By understanding what problems we are solving, we should be able to understand what type of data will improve our model. And what is a model? What type of algorithms are you going to use? And this is the last point in this playbook. Very often, junior machine learning engineers are going to focus on the algorithms instead of how to build a solution. But this is the least important part of the process. When we look at machine learning system design, we often care more about what is around the machine learning than the actual machine learning itself. And very often we can design solutions by thinking about the machine learning algorithm as a black box model that we can figure out later down the line. So let's look at a specific example. If you go on Facebook, you will actually notice that Facebook is recommending some friends that you could add. It appears in a tab, and we have a list of suggestions of friends that you may add. We have different friends, and if you go down the list, we have about 100 friends that may be recommended in that way. Every time you reload this tab, you will see that the list is slightly different every time. So if we had a product manager coming to you and asking, how would you implement such a solution? How would you do it? This is a question that I personally quite like because this is a question I got when I interviewed at Meta. So let's look at the business requirements. We want to recommend potential new friends to a user. What we want to maximize is the engagement on the feed because it is where the ads are. So in the long term, adding new friends will help maximizing the engagement on the feed and improve the probability that somebody click on an ad. So we need to understand the constraint. We have 1 billion daily users, and the list needs to appear in less than 100 milliseconds. So it has to be very fast. So how do we design a solution that solves this problem? So what is the ML problem we're trying to solve here? So here we have the list of profiles that are recommended, and the user may click on them or not. You can assume that there are some profiles that are more relevant than others because the user added those as friends. So what we would like to make sure is that the relevant profile are at the top of the list. We don't want them to be further down the list because the user will have less chance to discover them. We need a way to rank profiles. There are profiles that are more relevant than others, and we need a score that assesses the relevancy of a profile. The problem is very binary. Either we add a user as a friend or not. So this looks like a supervised learning problem. We learn a label, click or not. And by having people clicking on profiles, we get a feedback response from the user. Because this is a very binary problem, we could assume that we could use something like a classification algorithm or maybe a learning to rank algorithm. At this point, we don't need to figure out more. We just need to understand that this is going to be solved by a supervised learning problem that may be a classifier or an algorithm that is learning to rank. So what are our business metrics? We said we wanted to maximize engagement or maybe revenue, but this is somewhat vague to assess the performance of a machine learning solution. We need something that we can measure. So for example, we can measure the average time spent on the platform. We can measure the churn of the users. We can measure the engagement behaviors like clicks, comments, watch of reels. So there's a lot of things that we can measure to understand the improvement that a specific model may have on a user. So let's try to understand our online metrics. So in that case, we have users and they make requests to a machine learning model in production, and they get a response in a format of a list of recommended users. In the case of machine learning, we should have a way to assess what is a better machine learning model. So we should be able to compare models and have a metric for it. This is the online metric when we use production data. One way to do it is to do online experiments. So we can perform some online experiments to understand which model is better, and we need to have a clear metric that decides which one is better. So we need to be very careful in choosing that metric to make sure that it is in line with the business metrics that we are trying to optimize. One typical way to do it is to do a A/B testing experiment. So we carve a small amount of users from the user pool, and we reroute those users to a different model, a model that we would like to assess. And we compute some online metrics to understand how the models are performing. And we can perform some test statistics to understand which model is better based on the online metrics. So there are many different online metrics that we could choose to assess the model, but one online metric that is a good choice, for example, is the average number of new friends that is added per session. Basically, with this specific online metric, we want to understand what is the model that is going to lead to the highest average number of new friends per session. So we're going to optimize for the model that leads to the highest number of new friends per session. And again, we could have chosen another online metric. So let's remind ourselves, the business metrics that we want to improve is the time spent on the platform. Maybe we want to reduce the churn. Maybe we want to improve the engagement on the feed. And we chose an online metric that is the average number of new friends per session. The question that we may ask is, are those two metrics correlated? If the online metrics decide that there's a model that is better than another one, would the business metrics choose the same machine learning model if we could compare those models using business metrics? It is actually hard to know, but we need to do some kind of leap of faith to assume that what we maximize with online metrics would be what we would have maximized with business metrics. We can easily build a narrative on why these specific online metrics could improve the business metric, but we will not be able to directly assess it. In the end, we can only measure the improvement in business metrics and how it tied on to the machine learning solution. Let's now jump to the offline metrics. When we train models, we need to assess the models on historical data. Historical data is production data that we've seen in the past and where we got a response from the user. So for example, we showed the user a list of profiles and the user clicked on some of the profiles but not the others. The way we know that the profile is relevant is because the user clicked on it. We just know that the user clicked on those profiles. But let's say that we want to test a new model and we only have historical data to assess that new model. And let's say that the new model is providing a different ranking of the profiles. How do we know which profiles the user would have clicked? It is very possible that the new model is presenting in this list profiles that were never previously seen by the user. So if we never showed those profiles to the user, how will we know that the user would have clicked on it or not? The only thing that we know on historical data is that we showed some profiles and some profiles were clicked and some profiles were not clicked. So the only thing that you can do on historical data is to use the binary aspect of the response from the user. So it's not always easy to use the same metrics in online experiments than offline experiments. So when we have a binary response this way, it's actually easier to measure metrics like AUC, so area under the curve, log loss, or precision recall AUC. And this is typically the type of metrics that we use in offline experiments. I would categorize those as machine learning metrics. They are not very meaningful for the business, but they are easy to measure on the binary response that we have from the historical data. Okay, so we had some business metrics and we had some online metrics. So we already questioned the fact that those metrics may not even be correlated. So what about the offline metrics? Is AUC correlated to the average number of new friends per session? Is log loss correlated? So if my offline metrics were to decide that a model was better than another one, would the online metrics decide the same thing? It is actually not a guarantee. So it is almost an art to choose the right offline metrics such that they correlate with the online metrics. For example, when I was working on ads ranking, for offline metrics we used log loss. But for online metrics we used a revenue score for ads. And we realized that log loss were not very well correlated to revenue scores. And there were a lot of research and development to understand what would be a better offline metrics that would correlate better to the online metrics that we were using in online experiments. It is very important because we choose a model based on offline metrics and then we assess that model on online metrics. And very often the online experiment would fail because the online metrics would not provide the same results that the offline metrics would provide. So we would waste a lot of time to find the model that succeeds on offline metrics and on online metrics. So it would be great to find an offline metric that would give you the same result on online experiments. And it's not a trivial task. So let's look at the architectural components. There are a few questions that we need to answer. Does the solution needs to provide real-time inference? Or can we have batch inferences, meaning that the predictions are computed in a batch way? For example, they could be computed on a daily batch. Maybe we could have different strategies for different users based on activity. Some highly active users, maybe we could have some real-time inference for them, and maybe we could batch the inferences for the low active users. So we could choose different strategies based on the problem. When you think about the problem of suggesting Facebook friends, this is not a critical feature for the operation of the business. Do we really need to have real-time inference? Maybe we could have an hourly batch for the active users. When you design a solution, you don't need to have all the answers right away, but you need to understand what could be the options, and you need to find a way to assess quickly what would be the best option for your solution. So here we establish a couple of options, and we may need to discuss those options with different teams to see what would be the best option for our system. Very often it is easier to be conservative and to choose the easiest option, the one that is less costly and that would be implemented the fastest. Batching the predictions is often easier than to implement a real-time inference system. When it comes to the different functionalities that the system will need, well, we will need to be able to select the candidates. So there will be a candidate selection process. We may need to implement some filtering process. There are some users that may be blocked. There may be some privacy policies that prevent us from showing some of the users to some other users. So we may need to make sure that there is a module that takes care of filtering the resulting candidate selection. We will need to rank. Selecting the right users is not the only thing that we need to do. We need to make sure that we rank at the top the best users and at the bottom the less likely users to be added as friends. And we need to add diversity. We saw that when we reloaded the tab, the list of users that is presented is not always the same. And this provides a better user experience. If we are not always shown the same users, then we have more opportunities to click on different users. And this improves the ability for the user to provide a feedback response from what the system is providing. So let's think about the process from all the users that are available on Facebook. So on Facebook, we have about 3 billion users, so 1 billion daily active users. So how do we move from 1 billion active users to, let's say, 100 users presented on the screen? So there's the first step that needs to happen. We need to have a candidate selection step. We just select the relevant people for the user. There might be many different ways to do it, but let's assume that in average, a user has 1,000 friends, and we choose the second-degree friends in the network graph as potential candidates. 1,000 times 1,000 gives us 1,000,000. So by just choosing the second-degree friends in the network graph, we could move from 1 billion users to 1 million users. That's one way to do it. Then we need a ranking piece. We need something that takes those candidates and ranks them from best to worst. We rank them based on the propensity to click and keeps only the top users. Then we will need a filtering process. We need to filter away the people that have some settings that prevent them from being presented on the list. And we need to have a way to add some diversity. So we need to have some diversity module. We need to readjust the ranking to present different users every time. And this funnel will take us from about 1 billion users to about 100 users. So let's try to understand how we would build the system if we were to do real-time inference. A user requests a friend's suggestion on the Facebook servers, and the Facebook servers are routing the request to the candidate selection module. And we could imagine that a simple candidate selection process could be the second-degree friends on the network graph. So this process does not allow us to suggest out-of-network friends. But this is one way to do it, and we could think later down the way how to include out-of-network profiles. Understand that selecting the second-degree friends from a database would be extremely quick. Once we selected those second-degree friends, so let's say that now we have about 1 million or 100,000 users, well, a typical process is to rank in stages. We would have a light ranking stage and we would have a heavy ranking stage. The light ranking stage is very fast and can handle a lot of users, whereas the heavy ranking stage would be much slower but would provide a more accurate ranking. A light ranking stage would be done by a very simple machine learning model, where a heavy ranking stage would be done by a more complex machine learning model. So we could imagine that the light ranking stage would take about 1 million users and would select about 100 to 1,000 users. So with the light ranking stage, we want to make sure to capture all the relevant users. The ranking is going to be bad, but by selecting the top users, we assume that we're going to select a lot of relevant users. And the heavy ranking stage is going to rank those users from good to bad. This is where the machine learning happens. And then once we have a ranked list of users, we can add some diversity by adding some randomness to it such that the ranking is slightly different every time. And we can add some filtering process such that we are not presenting users that should not be presented on the list. And we are providing back that list to the servers such that they can be presented to the user. So we need that response to arrive in less than 100 milliseconds. That was the business requirements. To ensure that the response is very fast, then we will need a lot of concurrent machine learning servers to handle the load. This might be quite costly. So to handle 1 billion daily active users, we may need a lot of servers, and this will likely increase the cost. So we need to think about, would the cost of added servers really worth the gain that we would get with that feature? So that's why it's important to have some understanding of the potential monetary gain that this feature will provide. This way, we are not implementing a solution that is more costly than the reward. Additionally, we could assume that once we provided the ranking, we could cache the results for the next hour or the next day, such that the next time the user is requesting a friend suggestion, we pull from the cache instead of asking to re-rank again. We also need to think about how we're going to acquire the training data. And the training data is going to come from the response that we get from the user using the tool. So every time that the user is interacting with a feature, the friend suggestion list, then we need to capture the interaction that the user has with this list to reformat the response into a training data. So what would happen if instead of real-time inferences, we would batch the inferences? Well, we could assume that we have some kind of orchestrator, some batch generator, and we could assume that on a daily basis, for example, that the orchestration system would call for the ranking process, where we would have the candidate selection process, the light ranking process, the heavy ranking process, and the diversity and filtering process. So very similarly than in real time, but everything is done in batch instead of real-time process. Think that in the batch case, that we will need to do that for all the billion users that are active on the platform every day. That's a lot of ranking happening every day. Many users are actually not looking at the suggested list every day. So there would be a lot of wasted computing that would happen every day for not a lot of reward. So in the batch case, we would have the generated list that would be sitting on a database, and every time the user requests a friend suggestion, then the Facebook servers would just look in the database to pull the friend suggestion list. And like before, we would have the same feedback loop to aggregate the training data. So what about we were to build everything in a streaming manner? So a streaming process is like a delayed real-time process. So there's some event on the Facebook website when the user is interacting with the website that generates a friend suggestion request. And that request is queued in a queue. And then that request is passed onto an orchestrator. And the orchestrator is calling for the ranking process. So the candidate generation, the light ranking, the heavy ranking, and the diversity and filtering process. Once this process is done, then the list can be passed into a database. The next time the user is going to come on the website, then the servers are going to be able to pick up the list that has been generated previously. We could assume that the event that called for a ranking could be that the user is going onto the website and is requesting a friend suggestion. So the servers could look into the database and pick up the suggestion list that is already there, and in the same time request a new re-ranking of the friend suggestion. And this way, the friend suggestion list would be available for the next time. This could be a better middle ground. We only perform the ranking process for the users that are active, the users that are on the platform and requesting a job based on their activities. But we don't need as many servers because the ranking process can take a longer time. We just need to accept the fact that the ranking may be outdated considering the current context for the requesting users. It is very likely that a hybrid solution between streaming and batch would be the best solution here. We have some batch processing to make sure that the ranking is never too outdated, and we have some streaming process to make sure that the load on the ranking servers is not too high. And again, we would have the same feedback loop to aggregate the training data. So let's think about the training data. So where does come from the training data? Is it coming from the feedback loop of the user interaction with the suggestion list? We need to be careful about the way we aggregate the training data based on the specific solution that we chose for the architectural components. If we chose a batch process and the features are outdated compared to the time the user is interacting with a list, how do we aggregate the training data? We need to make sure we understand when we capture the features. The context for the user may be current, but the time where the features are being aggregated is somewhat outdated. In real time, the features would be current, but in batch or in streaming, the features would be outdated. There will be a delay between the time the features are being computed and the time where the user is interacting with the list. So we need to take that into account where we're thinking about aggregating the training data. So what do we do when initially there's no training data? How we build an initial product when we have no initial response from the user on that product? How do we generate that initial training data? Do we do it at random and get some response from the user and see what happens? So we need to think about the cold start problem. So what is the instance target? Click or not? We could imagine that there could be a more complex instance target. We could imagine that we could weigh the different instances differently based on the specific context. Should we choose all the instances presented to the user? Are the 10 first instances okay? Are the 20 first instances okay? Should we choose as part of the training data the instances that are down the list that the users never saw? So we should be careful about the way we select the instances that will be present in the training data. We should make sure that the instances that we are including in the training data has been shown to the user. Should we have different training data based on the different devices? The window in which we are presenting the instances will be different on a mobile than a desktop. On the desktop, I have more chance to see more profiles than I see on a mobile. So should I differentiate the way I aggregate the training data based on the different device that the user is using? Based on that, do we need a maximum window of instances that we select based on what has been shown to the user? Are the profiles shown at the top of the list similar to the profiles that are shown at the bottom of the list? Should we consider them the same for the training data? So we need to think about that when we aggregate the training data. So when it comes to the data, we need to think about the features. Typical machine learning engineers would want to have all the possible data available from the system. But as a machine learning system designer, it is important to figure out what would be the minimum features that you would need to have a successful product. And it is important to understand the problem you are solving to actually figure out what would be the features that would get you to have a successful solution. A typical strategy to understand what would be the minimum features that you would need to have is to think about the different actors that are at play in the problem you're trying to solve. Here in the Facebook friend suggestion problem, we have three different actors at play. We have the user that is requesting a suggestion of the potential friends that he could add, and we have the potential friends. Those are two different actors that are at play in this problem. Additionally, we have the context in which the user is requesting the suggestions. Additionally, we have the user's interaction. So the features that could be related to the interaction that the user may have had with the potential friends that are suggested. Let's think about the potential features that we may have when it comes to the user. Well, we have the user ID. So the user ID is a sparse feature that could be translated into a vector representation. We have the user profile. The user profile could be translated into different sets of sparse features. We have the user picture. Again, we could translate that into some vector representation. We have the visited pages. So again, we could translate that into a time series of sparse features. We have the previously added friends. So again, we could translate that into a time series of sparse features, etc. So there's a lot of different features that we could think about one user. When it comes to the potential friends, well, we have the same features that we could add for all the different potential friends. The user ID, the user profile, the user picture, the potential visited pages, etc. And in principle, we have thousands of potential features that could be at play here. Additionally, we have the context. Is it summer? Is it winter? Are we close to a holiday? What is the current location of the user? What is the current time of the day? Etc. So there's a lot of context that could be added in terms of features when we want to train a model. Additionally, we could have some user-users interaction. So how many times did the user like other user post, the common groups that the users are, the fractions of common friends, etc. So those are user-user interactions that could be useful in understanding if the different users have an affinity for each other. Understand that there are potentially tens of thousands of potential features that we could add here. There is no need to list them all, but when it comes to building an initial minimum viable product, it is important to understand what will be the initial features that you would test in that minimum viable product. And finally, let's think about the model. The model, the specific algorithm we're going to choose, is the last aspect of that machine learning system design. This is the least important because we could iterate and we could try many different types of algorithms. This process never ends, and there is no one model that is always better. There can be some decisions that can be made based on the framework related to the model. So for example, it is likely that deep learning would be the best solution in that case. So if you decide that deep learning is the best solution for the problem, then you could build a lot of modules that relate to deep learning architectures. And maybe you can build a lot of automations based on the fact that you decided that deep learning was the best decision for you. When it comes to that problem, what we're doing here is a recommendation. So it is likely that the models that are going to work for you are going to be recommender models. And there's a lot of models that are known to perform better for recommender problems. When it comes to recommender system, deep learning is usually the king. And you may want to look at some modules of your architecture and have an automated way to test different submodules. For example, you may want to change from a convolution module to an attention module. And if you know that deep learning is a framework you're going to use, then you can really build a whole code base that will relate to the automation of testing different deep learning modules in your models. But this will come later down the line when you are more mature in the implementation of your product. So if we come back to the ranking process in our system, it is very likely that for the light ranker, you may want a logistic regression or a simple neural network. And it is very likely that for the heavy ranker, you may want a complex neural network. So a logistic regression is a very fast model, where a complex neural network is going to be slower at inference. So a logistic regression is going to be able to handle more candidates to rank, where a complex neural network is going to need to rank less candidates to be as fast. So here what we did with this machine learning system design on that example is very superficial. It is a high-level overview of how we're going to build the system, but each of the different components, each of the different aspects will need to be investigated further to make sure that we can improve the process. But a first high-level overview of how we're going to build things is helpful to start investigating when we want to build an MVP. It is also helpful to estimate a potential budget for that project. So I hope that this framework gives you a good overview on how you can design machine learning solutions.